In this series of lectures, we're going to talk about atomic structure and kind of the fundamental experiments that went into understanding the basic structure of an atom. And this series of lectures is coming from the floor of my bedroom, so my background isn't quite as interesting as my office, which is still not very interesting. But what we're going to do is first talk about a little bit of history about atomic structure. And there is so much to learn about this if you really enjoy the history of science. If so, let me know and I can point you into some resources. A lot of this work for what the atom looks like that we're going to be looking at, and Dalton's, that built up to John Dalton's atomic theory, was done around the 1800s, at the beginning of that century. And so this is at a time where the work of chemistry and biology and physics were all very intertwined, and these disciplines weren't as separate in their distinctions of what they're studying. And this work was done primarily by wealthy white men who were able to do that work. And so uh, the build up to our modern picture of what an atom is really took root in the just before the 1790s with the conservation of mass law. And so this stated that in a chemical reaction, matter wouldn't be created or destroyed. So if you created a closed system and a chemical reaction took place, it would weigh the same at the end of the reaction, even though it was an entirely different substance. And so that means that we aren't creating matter when we are doing these chemical reactions, which was fundamental to our understanding of atomic structure. Then later on, closer to 1800, the law of definite proportions was developed. And it states that all samples within a given compound, no matter what their source or how they're prepared, any of that, they're going to have the same proportions of constituent elements. Which means if I somehow figure out a way to synthesize sodium chloride, or if I extract it from an ocean, it will still have the exact same composition if it is sodium chloride. So whether or not that's man-made or found in nature, right? And so this idea of something being a chemical and that being a man-made thing disappears, right? That everything around us is a chemical, and so whether that's in nature naturally or if it's something that we create from materials from nature. Then after the 1800s, John Dalton proposed a law of multiple proportions, which basically just states that when two elements form different compounds, that the mass of that element A and B will combine in a way, well, they'll always be the same ratio of whole numbers. And this really gets to this idea that there is something fundamental about all of the different elements that we can't break it down further than that. And that really gives us that idea of the atom, right? That there's this indivisible unit that will combine in a way that will always be whole and multiples of itself. So that all comes together then by 1810, and we get this picture of the atom, and it's outlined in John Dalton's atomic theory. We call it Dalton's atomic theory. As four main points. First, that each element is composed of tiny indestructible particles, and we're calling them atoms. And so this is the foundation of chemistry, right? That we have these building blocks that make up different compounds and substances and matter. And those building blocks are atoms, and you can't destroy them. You can't cut them in half. Then that all elements of a given element have the same mass and other properties that distinguish them from the atoms of other elements. So a silver atom will be a silver atom, and it will have a mass of a silver atom, and that will be different than a gold atom, which will have a different mass, is the idea. The third one is that atoms are going to combine in simple whole number ratios to form compounds, that these Lego building blocks that we're calling atoms will stack and form and combine to create something that is a compound, and that it will only be able to make those combinations in whole number ratios. And lastly, that atoms of one element cannot change into atoms of another element. So within a chemical reaction, atoms exchange, they change how they're bound to one another, but they don't actually themselves change into another substance. And this makes sense in terms of organic chemistry, the field of synthesis for inorganic and organic chemistry that's built off of this, that we are changing how atoms are arranged relative to each other to form new compounds. However, this breaks down the second we talk about nuclear chemistry, where we do actually have something that is an unstable atom that releases energy and a radioactive particle and becomes a new atom. So this is, not a perfect theory, and it's, the 1800s. So some of the experiments, if you want to go dive into some Google holes and learn more about this, to think about the four experiments that really gave us this picture of an atom, was the cathode ray experiment. That was J.J. Thomson, and it led to the discovery of the electron, that there was this particle that was zipping around on the outside, creating the volume of the atom itself. And then Millikan's oil drop experiment, in combination with that, determined the charge of that electron, which was really powerful. And Rutherford's gold foil experiment gave us really the structural idea that there's a nucleus that's at the center of the atom that has most of the mass, and that the volume of the atom is mostly empty space. And so that, plus then Chadwick's experiments, which were several, he was able to show that that mass of the nucleus is not comprised just of positively charged particles to counterbalance our negatively charged electron, but also neutrons. And he showed the mass of a neutron and the existence of it. So that gives us this modern day picture of an atom. And we will go into the electronic structure of this atom in far more detail in this class. And we'll go deeper into what does this modern picture of how these electrons zipping around really look like. And then we'll start talking about quantum mechanics. And then later on in our series this year, we'll spend a lot more time on that nucleus, and we will look at that in Chemistry 163, and we'll really dive into what is happening inside that nucleus with those protons and those neutrons, and how can nuclear chemistry, nuclear chemical reactions take place. So let's just start with this picture, right? Let's put a little bit more detail on top of it, other than atoms have neutrons and protons and electrons. So they do. Those are the three subatomic particles that are kind of fundamental. And if you go take a physics class, you can go deeper into subatomic particles. But for the purposes of an introductory chemistry class, we're going to stop here. So we have three to keep track of within our nucleus. We have neutrons and protons, and our protons are going to have a +1 charge associated with them, and our neutrons will be neutral. Goes with the name, right? So that they're not a charged particle, but they have mass, and they have a very similar mass to a proton. And so these are really close. They're not exactly the same. And so having that positive charge does change the mass of the proton versus the neutron a little bit. And here we have them in kilograms. We also have atomic mass units, which is a different way of a different unit for measuring mass that's not part of the metric system. But that is used a lot in chemistry as it kind of evolved from these old ideas of the structure of an atom. And so these two components make up our nucleus together, and it's at the center of the atom, and it's very, very small, and most of the mass of the atom is tied up in that nucleus, because when we look at what's around it, it's just electrons. And you'll note that we actually call this an electron cloud, and so it's kind of taking up this general space here. And it's going to have each electron will have a -1 charge, but come and look at its mass. It is tiny. It is much smaller than the mass of a neutron or proton. And the mass of all of these things is extremely mind-bogglingly small. But that difference between the mass of the electron and the proton or the neutron, it really becomes a rounding error when we're talking about reporting the mass of something on a larger scale, like the mass of lots of atoms of something. And so we say that the mass of that electron is negligible. Like it's there, it exists, but in all of our calculations, it's not going to have a meaningful impact on what we're using the mass of this particle for. And so we think of it as it's still matter, but it's so tiny and it's so light that it starts to have different behaviors than we expect for something heavier. And we'll talk about that quantum behavior again later. I'll get more into it. And so this electron cloud, though, one of the things, and this is something we'll talk about in more detail, we don't say that there's a specific volume to this atom. Instead, there's a area around the nucleus with a higher probability of finding electrons. And the further out you go, that probability decreases. And so we usually think of that size of the atom as being a certain percentage likelihood of finding an electron in a space around the nucleus. And a way to kind of visualize that and simplified is to say there's this cloud of electron probability. But then you kind of translate and you're just kind of envisioning this cloud around a little speck of a nucleus, which is more or less kind of the easiest way to think about it.